Thanks for deciding to stay here. I hope you remain in this room. I will do my very best. So my discussion today, my talk will be about building and running scaling enterprise LLMs or FinLLMs if you want, using open source software and accelerated computing. So just a brief company introduction. I think everybody knows that NVIDIA is somehow associated to gaming, to GPUs, which is this graphics processing units. Maybe what's not so well known is that NVIDIA is also producing a lot of software. And this software I will present today. And we also accelerate open source software. And this is basically how we build an enterprise AI platform today. So we also develop SDKs. We pre-train models, so people can just leverage pre-trained models. For example, for computer vision, we also have a foundational large language model called Nemotron. So there are many, many models out there that can just be downloaded and further fine-tuned downstream in your processes. So NVIDIA is sort of a platform, an ecosystem. Lots of developers around the globe leverage our platform. And it's not only AI, right? It's also data processing, it's simulation, and we see more and more use cases also in financial services where you combine those platforms for AI, high-performance computing, and visualization. So just a little bit of background stories on how ChatGPT started. So there's this story about a small startup approaching our founder and CEO Jensen in 2016. He heard about GPUs and that we built these boxes there on the right-hand side, DGX. So it's 8 GPUs connected. So that was actually built for internal purposes by our engineers. But this startup person insisted on getting one of these boxes and eventually getting more of these boxes. In the end, it was the co-founder of OpenAI, Elon Musk, and this was the birth of NVIDIA entering the Gen AI business, and now it's like 90% of the world's AI infrastructure, basically. So OpenAI, for example, initially was trained on 10,000 GPUs, and all the public cloud service providers have hundreds of thousands of these GPUs available for internal purposes or for users like us. By the way, the DGX is also available as a DGX cloud, so you can just go to one of these cloud service providers and build your own ChatGPT if you need to. So why is this GPU computing so important, and why is it so successful, and why is it enabling generative AI? It's because it's accelerating the workloads. We relied on many years on CPUs, which is a sequential computing model, and it's too slow, right? It's too slow for the huge models. So we started to build these GPUs. There are other accelerators, but I think GPUs are the most popular, well-known ones. So the principle is very easy. Whenever you have workload which is highly parallelizable, you can offload that workload to the GPU. It could be a Monte Carlo simulation. It could be a deep learning training. It could be inferencing. So that 1% of the code that takes 99% of the time, you want to identify this and offload to an accelerator like a GPU. The rest remains on the CPU. So it's always a computer that leverages CPUs, GPUs together. And since these models, like large models, are so big, it's not enough to have one GPU because it does not hold the model. Ideally, you would use many GPUs together and network them very quickly. So that's how you build and train and infer these large models. So this acceleration technology, it has sort of changed the economics of the data center fundamentally. These are just ballpark figures, right? So on the left-hand side, you see the sequential computing model, and here the purpose is to build one large language model, training, for example. You would need around like 960 CPU servers. Now, if you want to go for a computer that uses the exact same amount of energy, and you switch to the GPUs, you will be able to train 150 large language models. Or if you want to spend the same amount of money, then you would go for GPUs, and it's like 44 LLMs instead of one being trained. So you can get more for your investment. Or you're really just interested in building one large language model, so you can do it with like 2 GPUs. And it's much cheaper and using a lot less energy. So just some ballpark figures to highlight how the economics of the data center has changed. It's triggering an industrial revolution, actually. And this applies to the data centers in the public cloud, but also on-prem data centers, wherever these GPUs reside. And also, it's important to note that this not only applies to training these large models, but also data processing, inferencing. These are all jobs that can be accelerated with compute. For example, we have this use case recently started with PayPal, who use one of our open source data processing libraries, and they could reduce their cloud spend by 70%, 70, right? So you see customers use this GPU power in very different ways. So talked a lot about hardware. Now I promise we'll talk more about open source software. So by the way, it's a fact that I frequently mention because people are not really aware of this. So 70% of the NVIDIA engineers are actually building software these days. So NVIDIA is a hardware software platform company. And you all know the left-hand side, right? So that's like ChatGPT, Gemini, all these API-based models that are very easy to use, very convenient to set up use cases with. And this is something that NVIDIA supports, obviously, because it's powered by our GPUs. But today I want to talk about more on the right-hand side, where you use open source models, community-based models, and software to really own the model yourself and fine-tune the model, maybe connect it to your enterprise data using retrieval augmented generation and all these nice things. And this is where we have built the so-called NVIDIA NeMo framework, which is an open source framework for training, customizing, and deploying large language models. So you have a number of components and software suites that you would need for the training or the fine-tuning and the inferencing. One of them is the so-called RAPIDS library, which is accelerated data processing, ETL. Like for those of you who know Spark or Pandas, this you can use without code changes and accelerate with the GPUs. Then there's the NeMo framework. I will talk about this in a second. And on the inferencing side, we have 2 interesting open source libraries called TensorRT and TensorRT LLM, obviously. And we have the Triton inference server, which is one of the most powerful inference serving open source platforms available. For example, if you use the word autocorrection in Word, this is powered by Triton. Or if you swipe your credit card and there will be a complex fraud detection in 2 milliseconds or below, this is NVIDIA GPU and Triton inference server. Or if you buy stuff on Amazon, you get a recommendation of next best product. This is recommendation engines powered by Triton. So it's a very popular and very powerful framework. So NeMo specifically is a collection of tools that can be combined via API gateways, for example. So it would be helpful in data acquisition, data curation. There's a so-called NeMo data curator, which is open source, which helps to clean up the data and make the data in a form and shape that you can really do your fine-tuning, for example, and improving a Llama model, for example, or customizing a Llama model towards a financial large language model. A lot of customization techniques are available in this framework. There's also something for retrieval augmented generation. And we have the inferencing platform, which consists of TensorRT and the Triton inference server. And we also created a new open source project called Guardrails, which is NeMo Guardrails, which is exactly doing that, guardrailing a model in terms of the domain, safety, and security. And this is quite popular, so a lot of startups and ecosystem participants around AI observability are starting to use this project. So data curator, just very quickly, for fine-tuning, if you want to, for example, filter your data or deduplicate, so, or even tokenization jobs, right? This is the right tool. So here is where you do this data curation at scale, and it's GPU accelerated. So that means you can save a lot of time and money while you prepare your data in a way that is suitable, has a high quality to fine-tune. Then, if you really decide to train your own model, which some have done in the past, there are a lot of tools here to parallelize your training. These sort of tools, for example, were used in the Bloomberg GPT, where we support it. And recently we have seen also new data sets being explored, where you are really in the need to train a model from scratch. For example, an order book GPT or a payments transaction data GPT. There are no community models out there, so you need to train this model from scratch. But I think most of the companies that doing large language models are happy with either the API-based models or Llama style or Mixtral or these community-based models, so there's no need for training models from scratch. I just wanted to highlight that these things exist. Yeah, I think I briefly mentioned the guardrails. So it's something that helps you guardrail the model in terms of topical, safety, security. And by the way, this open source project can be combined with models like ChatGPT or any other large language model that you have. Of course, you can also take a fine-tuned Llama model and combine it with the guardrails tool. So it's programmable guardrails. Now coming to the inferencing part. So it's a very challenging exercise. Now that we see that more and more of these large language models go into production, people understand that it can be very costly to operate and deploy them and to run them and maintain a good level of low latency, maybe high throughput when you have more and more users. So we see that banks, for example, now turn to these tools that I already introduced a little bit to have a cost-effective deployment, right? It's a challenging exercise, inference, and bringing the models to production, because there are so many aspects that need to be combined here. You have certain constraints in terms of latency or amount of users. There are all these different frameworks out there that you maybe used for building your model, like TensorFlow, PyTorch. You need to find the right processors. It could be a CPU, it could be ARM or x68 CPU, or it could be different GPUs. Some of them are very well at inferencing, for example, L40S. Then there's a middleware, obviously, that you need to consider, and you have very different kind of models, transformers, RNNs, CNNs. So this is really a very complicated way things to look at when you do the inferencing. And one of the tools that really helps here is TensorRT, because it sort of optimizes the model before you deploy it, which saves a lot of time and makes the model faster and less cost intensive. So TensorRT, it can be used for any deep learning model, but TensorRT LLM obviously is designed for large language models like Llama, for example. So here you see some performance measurements. So this gray boxes, that's the A100 GPUs. Then you might switch to the H100, which is the most recent or the more recent card, and you see already an acceleration in Llama 2 of 2.5 in the inferencing of a Llama 2 model. Now, when you employ this TensorRT LLM software, which comes for free, you can accelerate to 4.6. Just an example, right? And this reduces your cost tremendously. Total cost of ownership can be reduced. So TensorRT, powerful framework that can be combined or used or applied to many of these open community models. Now comes the Triton inference server. So this is after you have optimized the model with TensorRT. And again, this runs on a lot of cards. It could be even CPUs, could be GPUs. And it's a scalable multi-framework for inferencing. So you can manage very easily your latency, budgets, your throughput objectives, and all these things. So Triton Inference Server works on many of these frameworks. It even works with tree models like XGBoost. So you could inference these models. And it can be optimized in certain directions. It can be combined with these MLOps tools that everyone uses. It's a microservice in Kubernetes, so it's very easy to deploy on different infrastructures and to manage. And it's optimized for high performance, right? Best utilization of GPU and CPU. This drives down the TCO. Again, it's open source, and it's also an entire ecosystem that we work with. So in the cloud, obviously, these Kubernetes integrations with MLOps providers, so you can combine it with your infrastructure very easily, right? It runs in every cloud. So the NVIDIA software, by the way, is agnostic. So that means runs the same on AWS, on Google, on Azure. So you just need to find the GPUs in these clouds and then download our software and merge it, combine it, and then you have the NVIDIA accelerated computing platform. And once you decide to switch from Google to Azure to AWS to Oracle, you can do it. And if you even decide to have an on-premise GPU cluster for cost reasons or data security reasons, you can do this and run the software on the GPU cluster on-prem. Good example, I think, is the BNY Mellon case, who really built an AI factory. They have an on-prem superpod that they run where they use the software of NVIDIA, and they can also use that in the cloud. So they built a hybrid approach, and the software stays the same everywhere, right? So I think that's the future, having sort of a portable platform that builds multi-cloud hybrid and makes best use of the compute power you have underneath, because that's a huge cost factor, again, in these large models, right? So for those of you who are interested, there are more features which are not open source in the NeMo framework, and you can basically combine them with these API gateways. One of these focus projects that we have is NVIDIA NIM, called NVIDIA Inference Microservice, which comes under a license. But basically under the hood, it takes Triton Inference Server and it takes TensorRT LLM. The NIMs make any large language model like Llama available in like 5 minutes, and you can get much more tokens out of a Llama, like 3 times more than just using the plain vanilla GPU implementation. So the open source variation or variant takes more time. It takes like 2 weeks or so to fine tune and to set it up for the right infrastructure. The NIMs do this automatically. So they find a certain GPU cluster infrastructure and they automatically run the right, it's like a model to go if you want. So it's a time benefit deciding for the license or going for the completely free open source. This may be interesting for getting started very quickly. So this is ai.nvidia.com, where you can basically test NeMo, and also you can decide to start with a Llama model or with a Mixtral model, or Nemotron, which is our own foundational model that we trained, or Falcon, or all these, or Llama, so all these nice community-built models. And then you can customize these models using the NeMo framework that I just presented. It's open source again. And then if you really want to go into the production, you can use the license and run these NIMs, or do it yourself, which takes a little bit more time. One of the cases I already mentioned is the American Express, who use the inferencing server and the TensorRT, so that they are really able to screen huge amount of data in like 2 millisecond complex fraud patterns, including graphs and networks, payment networks, graph neural networks, to identify fraud in almost real time. So this is how this could be used. The other obvious case where inferencing really is important in terms of low latency is the experience that users have with a large model. So the large model needs to answer within, like, I don't know, 300 milliseconds, otherwise you would not use it, because it's no fun to use it, right? So first time to token is important, or time to last token, so all these metrics, right? So that's what you want to optimize, and also the throughput, like having a lot of users on your system. So this is the idea of these NIMs. I mentioned it. So we want to really connect those model builders with all these community models, where like every day is coming a new model, I think, with the acceleration infrastructure, GPUs in the cloud, on-prem. So that's how we connect these millions of developers to these millions of GPUs. And with all these layers of data platforms and tools that can be combined with this. So that's the vision where we are currently working on. So just very quickly on the rapids part, because I think that's an important discussion. When I go to, or when we work with banks, sometimes they want to build these LLMs, but maybe they are not mature enough yet. So first of all, they want to save some cost and maybe clean their data and tidy up their data processing steps. So this is where we then suggest using rapids. And again, it's completely open source. It is basically a suite of GPU-accelerated libraries that have APIs that match most of these popular open source tools. So it can be used to accelerate data frame operations, some SQL operations even, Spark workloads, but also data frame operations like pandas, for example. And it's available in all these tools like Databricks, Cloudera. It can be used in the cloud. But basically, it's this rapid accelerator for Spark. That's what is behind there. So the idea is to look at a typical workflow here, where you prepare the data with pandas, then you train some model with XGBoost or use scikit-learn. Then maybe you have some graph analytics with network X, for example, transactions networks. Or you train some deep learning model with TensorFlow and PyTorch. And in the end, maybe you want to visualize and filter a huge amount of data. So that's all great packages in Python. The only caveat is it's bottlenecked by CPUs, right? So it's expensive, it's slow. And the idea is to switch to these equivalents, these libraries like pandas, for example. You can accelerate with the GPUs without code changes. It's the same API. Network X is also the same, XGBoost. So you just select GPUs instead of CPUs. And if that's still too slow, you can use more than one GPUs using the Dask frameworks. So really accelerating end-to-end this stuff. And by the way, if you really manage to run the entire pipeline from data preparation to model training to visualization on the GPU, you get an additional booster because you don't need to copy data between GPU and CPU. So you keep everything in the GPU memory or even connected memory of several GPUs. And this is how you can accelerate basically the entire workflow. And again, I mentioned the use case with PayPal, who managed to reduce their cloud spend by 70% with this Rapids framework. So here are some examples. For example, if you want to cluster data with dbScan, it's an average speed up of 50x with certain example data sets. Or if you want to accelerate XGBoost, there's a speed up of 10x. Some people use hyperparameter optimization for XGBoost. So that's another thing that can be done on one or more GPUs. QGraph, you are able to process a huge graph and networks, like trillions of edges, for example. It scales, putting more GPUs, and there are also some SQL Spark workloads that can be accelerated. So this is a typical workflow here where you have data loading, data conversion, and XGBoost. You will find this a lot, I think, in the machine learning departments. And you see that when you add more and more CPUs, yes, it's getting faster, but not really that much, right? You put 20, 30, 50, 100 CPUs, but it's just not getting really fast. So when you switch here to the GPUs, it takes like a few seconds compared to a long time. And this is the secret behind this cost saving, right? Because the GPU is done in a few minutes maybe, and then you can just switch it off or use the GPU for another workload. So that's the idea. It's your data science at scale with really huge data workloads. There are a lot of examples here of algorithms that we implemented, community detection or PageRank and all these things when you have huge payment graphs, for example, like in fraud detection. And you can also combine these QGraph network X with graph neural networks. So deep learning and network analysis combined. So we accelerate these like two libraries, PyGNN ESG and deep graph library. So I think this is what you can use for very sophisticated fraud detection applications. Another use case would be explainable AI. So for credit scoring, for example, you would need to extract explainability information out of an XGBoost model post hoc, so post training, and we accelerated the XGBoost Shapley values, which is one of these methodologies to make a model more explainable. So this entire workflow is also on the GPU, and this bank that we worked with, it took them very long time, like several days basically, to compute their entire credit portfolio, extracting the explainability information, and now it takes them a few minutes. Similar use case we did with a Munich Re, and they used the Rapids for explainable AI for diversified portfolio construction, and by using some GPUs they could accelerate the entire process. So now they are able to come back with an answer to the customer the same day. What's the best portfolio construction algorithm I should use in my portfolio? Before that, it took them several days. So this is the overview in the end-to-end solution, starting with Rapids to do the preparations, then maybe train a large model or fine-tune a large model or train some deep learning, PyTorch, TensorFlow model maybe. Then the application of these optimization for inference, which is the TensorRT or specifically TensorRT LLM. And in the end, you would use the Triton inference server. And this is all the open source packages combined for an accelerated end-to-end solution. Just to mention, some people in finance are very interested in ESG, so they want to process spatial data, Earth observation data, and there are some interesting libraries. Some of them are part of Rapids, some are not, that help you to process geospatial data at scale. For example, in this picture you see some radar data that we processed, and we could accelerate by factor 269. The amount of data points that needed to be processed was 500 million, right? So you see it's faster and maybe better resolution for your use case, and it can be a cost saver, really. Just an outlook here, we are also contributing to a project called Earth-2, which is sort of a project to better understand our atmospheric digital twin of the Earth, combining simulation, physics, machine learning, generative physics, AI, and visualization. So all this can be executed on NVIDIA platforms. And the key library here that we use is Modulus. So Modulus has all these fluid dynamic libraries, but also it has physics AI libraries that allow you to predict the weather with AI and create large ensembles, and also to downscale weather predictions. So this is very interesting for insurance companies, for example, but also it's interesting for trading, right? To better understand impact of extreme weather on financial markets. And here's an example. So with supercomputing and this library, which is open source, Modulus is open source, you can basically reduce the cost of generating ensembles. So ensembles are like potential outcomes of the weather, which are physically feasible, which are realistic. And with a normal compute power, you would, for example, be able to predict like 50-member ensembles. So you would see how the hurricane or typhoon or whatever, which path it would take, right? With accelerated computing, you can generate with the same amount of time and invest like 1,000-member ensembles. And here you see that there are completely new trajectories with extremes. So you realize that the hurricane could also go to the mainland of US, right? There's a certain probability here. So this will sort of revolutionize the AI weather business. So it's basically generative AI applied to physics. And we see now the first use cases being applied in trading, investment management, and also NatCat and energy insurance business. Here are some examples as a final slide almost. So again, we have some companies that build models from scratch if it makes sense, like the Bloomberg GPT, they can use the Rapids framework. We have some partners like Deutsche Bank that built a FinForma model, a financial large language model, but also use the GPUs for simulation, for Rapids, also data processing to save time and money. And on the right-hand side, and this is really interesting, we have this reference with the BNY Mellon, who built this on-prem and sort of also hybrid approach where they use the NVIDIA software to be able to systematically analyze 600 AI use cases to identify is there really a POC or not. And once they have identified, they can use the same scaling platform to use these models into production. So for them, it's a really an AI, sort of an AI factory. So they see AI as a productionized factory where you optimize the assembly lines, minimize the cost, minimize the energy consumption, and sort of minimize the time to insight and time to market. So this is really, I think, a very good example of how this AI sort of project could be used in banks. Last slide. For those of you who want to try this, there's the so-called NVIDIA Launchpad. It's free. 1 or 2 weeks, everybody can test this. You can put the software that I just explained on the Launchpad and just test if this acceleration benefits your business or not. If yes, it's great. Then you can save money and time. If not, well, maybe next time. And also I wanted to highlight there's this Deep Learning Institute, a lot of resources on what I just talked about, courses, code books that you can execute, some of them even on Google Colab. And there's also GTC conference, which is coming up next year, which is one of the largest AI industry conferences. And we had a lot of banks there, a lot of US banks actually, not so much European banks, but I'm working hard to work with our customers that we have more applications from Europe, banks that really demonstrate their use cases and how they leverage this platform here. Thanks for your attention.